May 1944, the Ovitz family arrived at Auschwitz in a cattle car. Transylvanian Jews, they had been touring Hungary as itinerant musicians when they were rounded up by German troops. 7 in all, they were afflicted with a form of dwarfism that caused their limbs to be short and bowed. As the family stepped onto the tracks at Auschwitz, they heard a voice ordering them to move to the right. The voice belonged to Joseph Mengele, the so-called Dark Angel of Auschwitz. Looking down at them, he said, "Now I will have work for the next 20 years. Now science will have an interesting subject to consider."
This series is about the extremes of deformity, the limits of humanity. It's about the devices that go into making a normal human being and how they can be revealed by mutations. And we are all mutants. But some of us are more mutant than others.
The Ovitz family was saved from the gas chambers. Ironically, their savior was Joseph Mengele, a man whose name is now a byword for the perversion of science. He rescued them for his brutal program of experimental research. They were his laboratory creatures. But there was an even deeper irony. When Mengele asserted that the Ovitz's dwarfed bodies could reveal important things, he was right. And what the Ovitz family and others like them reveal is how we grow.
Growth seems very simple, just a matter of small things getting bigger. But in fact, growth is one of the more subtle and obscure processes that go into making our bodies.
This film is about the processes that control our growth. And it is about what happens when they go wrong. When they are driven from the proper course of development by mutation and disease. This film then is about dwarves such as the Ovitzes, giants and castrati. It is about some of the 1,000 or so genetic disorders that afflict our bones. And it's about how such disorders reveal the devices that regulate our growth. This film, then, is about the size we are. the size we all are.
I suppose technically I'm a giant. In the supermarket, and little kids come up to their mum and their mum and say, "No, Mum, there's a giant, Mum." And the mum says, "Shh, don't." And they look at me, awfully sorry. At the moment I'm 7'6.25", tallest man in Britain.
Chris Greener is certainly huge. I'm 6 feet tall, yet he dwarfs me. His gigantism has occasionally caused him problems, and not all of them are due to his height.
Back in 1971 I was having double vision, and I had my eyes tested, they were perfectly okay, and my doctor said I wanted to go and see this guy at Bart's Hospital. He looked at everything, and I mean everything. And I thought, hang on a minute, the old one-eyed trouser snake can see perfectly well, mate. It's the double vision's up here, pal. And he mentioned something about the pituitary gland, and I'd never heard of this. Didn't know what the hell was the pituitary gland, but no idea what it is.
But it is his wayward pituitary that links him to another London giant, Charles Byrne, who lived nearly 200 years before Chris was born.
Charles Byrne was born in 1761 in Ireland. His skeleton still hangs in the Royal College of Physicians and Surgeons in London, where he's known affectionately as Charlie.
Charlie died at the age of 22. It's thought that he drank himself to death. But this skeleton isn't actually Charlie's. The Royal College acquired his skeleton under dubious, not to say embarrassing, circumstances, and they won't let us film it. The story goes that Charles Byrne feared that his corpse would end up on the dissection table. He was right. When he died, says one report, anatomists surrounded his house just as harpooners would an enormous whale. Those are his feet you can see dangling in the top right corner of this picture. It's a portrait of the surgeon John Hunter, who got the corpse, boiled it down, and put it on display. It was only much later that someone worked out why Charlie was so tall. In 1911, Sir Arthur Keith, then curator of his remains, sawed Charlie's skull in half and looked inside. He found that the cavity left by the pituitary gland, normally the size of a pea, was in Charlie's skull the size of a small tomato. The pituitary is immensely powerful. It secretes growth hormone into the bloodstream, which then sends a simple message to the body cells: grow and divide. It is the multiplier of our flesh and bones.
I was told I had over 200 times the amount of growth hormone, and the results of these growth hormone that was obviously made me grow.
Charles Byrne and Chris Greener both had benign tumors in their pituitaries. In Chris, the swollen gland also gave him double vision as it pressed against his optic nerve. But if the pituitary exerts such power over the size we are, could it also explain why the oviducts were so small? The oviducts' smallness had saved them from the gas chambers, but turned them into laboratory creatures. Smallness has always had this socially ambiguous quality. Before their capture, the oviducts had been entertainers. They had a band, the jazz band of Lilliput, and made a living from their shortness, much as generations of dwarves had done before them. The court dwarves.
These days, we tend to view the court dwarves as being miserable and degraded creatures, stripped of all human dignity. But were they? And did they see themselves that way? One dwarf certainly didn't. For him, being small had been a gift, an opportunity. It had lifted him out of obscurity. His name was Joseph Borolaski. Borowski was born in 1739 in Polish Russia. The family was poor, almost destitute. And then Borowski was small. In his teens, he was only 2 feet tall. But he was bright, and he attracted the attention of a young noblewoman, the Tsarina de Karlioz, who took him up, educated him, and launched him on a glittering career throughout the courts of Europe.
Borowski ended his years in the cathedral city of Durham.
He'd had a good life, a rich life. Born in obscurity, he had known most of the crowned heads of Europe. He had married a dark-eyed young beauty, a noblewoman, raised children, and when he died at the age of 98, he had outlived most of his contemporaries. It was a graceful end to a remarkable life for Joseph le Comte de Borowski, last of the court dwarfs. So why was Borowski so small? Well, that perfection in proportion suggests one explanation.
Many types of dwarfism alter the geometry of the body. They cause the limbs to be stunted, the head to become bulbous, the nose depressed. Not so Borowski. He was normally proportioned, just small. The definition of a male dwarf is anyone under 4'10". At 4'9", Larry Nicholas is the tallest player on his team. Just like Borowski, he's perfectly proportioned, but the only court he's familiar with is the basketball court.
It's aggressive. The minute that whistle blows or the minute the ball drops, it happens, you know. Nobody's standing around patting each other on the back at that moment, you know.
As a child, Larry grew very slowly. It was suspected that he had a defective pituitary.
Teachers' parents noticed my pituitarism when I was 7 years old. That's when they got together, had a little meeting, and said, I think we ought to investigate Larry's growth spurts and see he doesn't seem to be going as much as the normal kids.
Either Larry's pituitary wasn't producing enough growth hormone, or else he produced it, but his body couldn't respond to it. Doctors put him on a course of injections.
Growth hormone did influence it, not at a rapid pace, not at a very fast pace, but I think it did push me along and get me up there.
It's impossible to say for certain that Borowski was a pituitary dwarf, but it's highly likely, because he was perfectly proportioned, just like Larry. By the 1940s, the role of pituitary growth hormone was well established. But the Ovitzes clearly were not pituitary dwarfs. Whatever caused them to be so short affected mostly their limbs. In searching for the cause of their dwarfism, Joseph Mengele x-rayed the Ovitzes, bled them till they fainted, and carried out repeated gynecological examinations of the women. Experiments that were fathomless in purpose, brutal in intent, and incapable of revealing anything about growth. Other scientists, however, were beginning to learn deep things about growth, but they were working on salamanders.
In 1768, an Italian scientist by the name of Larazzo Spallanzini discovered that if you chop the leg off a salamander, it will regrow it. Well, since then, thousands of the creatures have lost their legs to science. One luckless animal had its leg chopped off 20 times and regrew it every time. It's sometimes facetiously remarked among scientists that happiness is finding an experiment that works and doing it over and over again.
An American scientist and contemporary of Mengele's took Spallanzani's experiment, adapted it, and revolutionized our understanding of growth. His name was Victor Chandler Twitty. Twitty wanted to know whether animals had a single system that controlled growth, or whether every part, every organ, had its own controls. He took 2 species of salamander, one large, one small, chopped their legs off, and swapped the stumps from which the leg regrows. There were, he reasoned, 2 possibilities. The transplanted limbs might grow to the size of the host's legs, or they might grow to the size they normally do. To his surprise, Twitty salamanders grew up lopsided. The difference in their size couldn't be due to some hormone. Somehow each limb contained within it the makings of its own fate, its own size.
When it comes to growth, the organ that really matters is, of course, the skeleton. The skeleton determines our stature. Bones make us the size we are.
Many kinds of growth disorders, including the overtses, are caused by failure in the growth controls that are contained within each bone. But what are these devices, and how exactly do bones grow? To answer that question, we first have to find out how bones are made.
I'm in Cape Town, at the foot of Africa. One of the world's great harbour cities, it's where 2 oceans, the Atlantic and the Indian, meet. A city of immigrants from east and west, it's the setting for a remarkable story. The story of a family and of a society. And it's the beginning of our journey to discover how bones are made.
In 1951, an 8-year-old boy in Cape Town was kicked by a horse. X-rays showed an unremarkable leg fracture. They also showed something quite unexpected. Something unrelated to his injury. He had no collarbones. A scientific investigation began. Soon it was realized that the boy wasn't alone. In fact, there were hundreds of other people missing bones, and they all belonged to Cape Town's Islamic community.
We were always reminded, look, God created us. So, well, I felt proud of it, I must say, because I thought, well, it's something unique, something other people don't have, and I have it, you know. That's what I felt like. I got something which other people can't, you know, they don't have at all.
People like Sarodi and Ayam are missing bits from their skeletons. It's a condition known as Arnold syndrome, and it affects more than the collarbones. Many people with Arnold's have holes in the tops of their heads, just like newborn babies before the skull knits together.
Hello,
Professor
Mr.
Peter
Armand.
Bayton
Stop by.
has been studying this syndrome for more than 30 years.
Can I first of all see your hands? Can you do this for me?
People with the gene in this country have a bulgy forehead, pointed face. In the clavicles, there can be anything from absent to totally normal. Usually, and they can be asymmetrical. Usually what you find is a bit of asymmetry on one side and a bit of clavicle absent on the other.
Okay, my love. Can I have a look at your shoulders first of all? These clavicles. There we are. And this one's got a bit of a bump. So can you do that for me? That's it. Can you do that?
Arnold syndrome varies in severity. Nuran Arnold can pop out what's left of her collarbone.
This is sticks out quite a long way, doesn't it? Doesn't hurt though.
This X-ray shows the missing section. But in extreme cases, people with Arnold's can do this.
Oh, you've got a soft spot on the top of your head, all the way back there. The condition, although recognisable, is comparatively mild. In other words, technically there's no biological pressure against it. If you've got the gene, the probability is you'll hand it on to half your children, they will survive and hand it on to half of theirs. And they will recognise each other in the street.
People would come to me and say, which Arnold are you? And I would tell them who I am, or they would tell me again immediately who I am. And I have to ask them, who are they?
Allahu Akbar, Allah.
Everyone in the Cape who has the syndrome is descended from one man, Arnold himself. He was a sailor, perhaps Javanese or Chinese, and he arrived in the Cape in the 19th century. He took 7 wives and had many children. Now, about 1,000 of his descendants carry his mutation. The mutation was discovered in 1997. It disrupts a gene called CBFA1, which switches other genes on and off in the cells that make bones. Arnold's mutation stops this. The result is missing bone. But just as some people have a lack of bone, others have an excess. The consequences can be terrible. There is one extremely rare mutation which jams the switches controlling bone production so that they are permanently on. Here in Philadelphia, you find the world's leading center for research into this disorder and its most famous victim. It's a condition known as fibrodysplasia ossificans progressiva, or FOP. FOP is really one of the most enigmatic and horrible of bone diseases. It afflicted Harry Eastlack, who died in 1973, aged 39. He bequeathed a skeleton to science, convinced future generations of researchers would be able to solve the riddle hidden within his bones.
Harry's skeleton is an architectural nightmare. It is the skeleton of a normal man, which has been encased in another skeleton, but one that makes no anatomical sense whatsoever, a skeleton composed of arbitrary trusses, buttresses, traverses, and plates of bone. A skeleton that is pure anatomic irrationality.
Like Harry Eastlack, Carol Orzell suffers from FOP.
Most of me is fused together. My back from my neck all the way down is totally fused. Well, when I was a baby, I had lumps in the back of my neck that were really bad, and they were painful, and they were getting real red and sore, and I would scream because it was hard. And all I can remember is being in the hospital and me screaming. The doctor told my mother that I wasn't going to live for a very long time, and I wouldn't live past due. Well, I'm going to be 45 next year, and the doctor is dead.
In FOP, cells that should become muscle turn into bone. It's a rare phenomenon. We would no more expect it than we would expect the heart to turn into a spleen or else an eyeball. In FOP patients, the skeleton invades, even colonizes the body.
Children actually who have FOP, I guess the other way to look at it is essentially they form a second skeleton. Eventually, ribbons and sheets and plates of bone replace the body's muscles, ligaments and tendons, span the joints, and lock the joints in place, rendering movement completely, totally impossible. It's a truly catastrophic sabotage of the body's skeletal system. And in fact, any attempt to remove this extra bone leads to explosive episodes of new bone growth. Even minor things like preschool immunizations or an injection in the mouth for dental work can lead to permanent locking of a joint and the inability of a child ever to open their mouth again. Bone formation in an FOP patient is very similar to bone formation in a healing fracture. It's almost like as if the body misinterprets how to heal a wound. The first thing we see are battalions of lymphocytes. These are cells from the immune system that are coming from the blood, and they line up like very evil armies around the blood vessels in the muscle and destroy this muscle. Within a matter of hours after a flare-up begins, all you see is death and destruction of skeletal muscle.
A flare-up can be many things. It can come from a trauma of any kind, whether it be a bump, it could be just a minor bump, but with us, it might turn into something major, and it could go and flare up a bone in any part of our body at any given time. It doesn't have to be right at that point.
But what controls this process? We share over 90% of our genes with mice. They can help us answer this question by explaining the workings of a molecule called BMP.
What we have here is a pair of mice which have been the subject of an extremely beautiful experiment, one that tells us something very important about how bones are made. One of these mice, and they are terribly active, has been injected with a molecule called bone morphogenetic protein, or BMP, which is critical in making bone. And it's this mouse here. They are extremely active little animals, and you have to grab them by the scruffs of the neck, or else they will turn on you and bite you. There, got you. And here it is. This mouse has been injected with bone morphogenetic protein on the right-hand side. And as a consequence of that, just under the skin, it's grown a nodule of bone. And it's bone that is complete in all ways. It's really just like normal bone that you find in your leg or in your arm. The mouse is otherwise quite all right, and down he goes.
BMP is a signaling molecule. It tells cells to make bone. Genetically engineered mice in which BMP signaling has been disrupted do not form bone and suffocate at birth. They are extreme versions of what you see in Arnold syndrome. In Carol's body, a surplus of BMP activity means a surplus of bone. The two disorders are mirror images of each other. Together, they tell us how bones are made.
We have signals in our body that tell us to make skeleton, and we have signals in our body to tell us to stop making skeleton. And actually, the way our bodies are wired is that the accelerator pedal is connected to the brake pedal, so that we never can really get too far out of balance. So that when our body says it wants to make a new piece of bone, that's like the accelerator pedal, it also triggers the brake pedal to engage. What we've learned in FOP patients is not only are they making too much BMP4, they're not making enough of the stop-making bone proteins, proteins whose names are noggin and gremlin, for example.
The hope is that we will soon be able to reconstruct the complex circuitry governing BMP production, restore the body's natural equilibrium, and release patients like Carol from their living prisons.
Carol Orzel was the first patient I met who had FOP. She exemplifies, I think, what Faulkner said just before he received the Nobel Prize. He said that he believed that man will and mankind would not just endure, but that they would prevail. And I think that quotation exemplifies Carol's life. Carol doesn't just endure FOP, she prevails over FOP.
I don't let anything get me down. I just keep on doing what I have to do, however I have to do it. If there's something that I want to do or I need to do, I do it my best, and I like being independent.
In the late 1600s, William Harvey, the scientist who discovered the circulation of the blood, wrote that nature is nowhere more likely to show you her secret mysteries than in cases when she shows you traces of her workings apart from the beaten path. FOP is certainly apart from the beaten path. It's an extremely rare condition. There are fewer than 500 people in the world known to have the disorder.
It's almost like the Sphinx. There's riddles that skeleton contains that'll only be revealed if we ask the right questions. Very often, a new idea will pop into our mind, and we'll wonder, is this possible? Is this manifested in the skeleton? And we'll often carefully examine the skeleton, and almost always there is a clue on the skeleton or in the skeleton that we failed to see before because we did not ask the right question.
Here, as elsewhere, the pathological reveals the normal. Indeed, understanding FOP may eventually allow us to treat the 1,000 or so inherited bone disorders. We may even be able to engineer new bones in test tubes.
So what we have here is a collection of fetal skeletons. They range from about 2 months after conception at about monthly intervals until term, that is to say, until they're born. And you can see the skeleton, at first rather indistinct, but becoming ever bigger and ever stronger. Although they are indisputably human, it strikes you that they look a little evil, rather alien. It's those pointy faces and undershot jaws that give them a look of moral turpitude.
The skeleton is a latecomer to the embryo. An embryo has most of its parts. It even has fingers before it has bone. Bone emerges seemingly out of nowhere. It begins as undifferentiated mesoderm, a layer of cells in the embryo. Ghostly condensations then appear and transform into the vague outlines of a skeleton. Cells called chondrocytes make rubbery cartilage. Then other cells called osteoblasts deposit layers of calcium and minerals which form our bones. Then the skeleton has to grow, a process which is governed not simply by growth hormone itself, but many other hormones as well. The effect of just one of these hormones can be seen in castrati. And that's because boys who lose their testicles before puberty never stop growing.
In the 18th century, the monarchs of the great opera halls like La Scala weren't, as now, the tenors, but rather the castrati. Fated for the range, power, and unearthly quality of their voices, they bestrode the stage like colossi. When they sang, audiences cried, "Evviva il coltello!" Long live the knife, and swooned in the stalls.
In Italy alone, 4,000 boys a year lost their testicles for the sake of their golden voices.
This is a recording by the last castrato. His name was Alessandro Moreschi, and he was director of the Vatican Choir. He died in 1922. He's singing a piece by Rossini, and one has the suspicion that he's not doing it very well. It's awfully harsh on the ears. Now, it could be that tastes have changed, but I suspect that Moreschi simply was not a very good castrato.
I'm a mezzo-soprano, which is the middle female vocal range. Mezzos are the most realistic voice, similar to a castrato, in that their range is sort of the biggest, both on the bottom and the top. The Italians all knew about castrati. However hideous it was, they were part of everyday life. Their status was paramount. These guys were sort of the Jennifer Lopez of today. They were the people wanted to see. Their names sold opera. Their names sold these shows. I know that they were huge. I think they might have been quite extraordinary, and I would have loved to have heard one. I'd love to jump back 200 years and see one of them in action.
Nobody seems to have actually measured the castrati, but there's no doubt that they were immensely tall. This is an engraving, said to be by Hogarth, of a castrato, Senecinio, singing Handel's Flavio in Covent Garden in 1723. Now, the really striking thing about this is that he's just about twice as tall as everybody else. I mean, it's a caricature, of course, and a rather cruel one, but it does show the weird, elongate limbs that the castrati have, something called a eunuchoid phenotype now by physicians. It's the consequence of limbs that just don't stop growing at puberty. These guys kept on growing well into their 20s and even their 30s.
Analysis of the skeletons of eunuchs shows that even if they reach their 90s, they have the bones of adolescents. In children and adolescents, the skeleton grows continuously. It can do so because at the end of each long bone, a humerus or a femur, there is a region of soft, uncalcified tissue where cells multiply, the growth zone. In most of us, these growth zones seal up at about age 18, and we stop growing. Not so, however, in castrati. In castrati, the growth zones remain open, and they do so because of a lack of testicular estrogen. We think of estrogen as being a quintessentially female hormone, and so it is. It is the hormone of breasts, periods, pregnancy, and the menopause. But estrogen also stops bone growth. Deprived of their gonads, castrati have no estrogen, open growth zones, and become unusually tall. It's as simple as that. The body's logic is beginning to emerge. Our growth is controlled by hormones that influence the very cells of our bones. But mutations in any one of more than 1,000 genes can disrupt the growing skeleton. One of them is responsible for the smallness of the ovitzes. But which one? The ovitzes were obviously disproportionate dwarfs. Their disorder caused them to have short limbs even as it left their torsos, heads and faces largely unaffected. Their shortness could not have been due to a failure of the pituitary or growth hormone. The mutation had to lie elsewhere. The body, it seems, is rather like a country, with different layers of governance determining its growth. Some processes regulate the growth of particular organs, others do so for the entire body. All exist in a delicate equilibrium that can be destroyed by mutations in any one of more than 1,000 different genes. And most of these mutations make us small.
I'm in Reno, Nevada for the Western States Conference of the Little People of America. It's where the West's dwarves come to meet and mate.
Many friendships, romances, and whole families of dwarves can be traced back to encounters at LPA conventions.
It's like a needle in a haystack when you think you want to marry somebody of your own stature. You come to these events, it's like all the needles are there without all the hay, you know, it's right there. So it's quite a rich environment for finding a mate. I was going to marry whoever I fell in love with. And I dated a lot of average-sized women, but I did want to focus on trying to find somebody that was of short stature. And then when I found my lovely wife, Amy, you know, it was basically love at first sight. We met at a conference. She was in Michigan. I was in California. Never would have met had it not been for LPA.
Matt Roloff is president of the Little People of America, which was established in 1953. It held its inaugural convention here in Reno. When you see the dwarves, you notice the differences first, how they are so distinct. Some have stunted limbs, some bulbous foreheads, others have bent backs. But the curious thing is that the eye quickly adjusts so that very soon they seem to be just part of the spectrum of human diversity. In part, that comes from actually getting to know them. You quickly see that they are professionals networking, holiday makers relaxing, teenage girls flirting. They're just another slice of Middle America. Dwarf is a perfectly acceptable term to LPA members, and it's scientifically correct too, although many gathered here prefer the gentler sounding term little person.
Short-statured is politically correct. Dwarfism is politically correct. Midget is not accepted right now. It's not a term that a lot of our people are deeply hurt by the term midget. Primarily it's because of how it's used. Hey, look at the midget, you know, and it's sort of a derogatory tone in people's voice when they use it or say it. So that's primarily why I think that word has become negative in most circles.
A lot of the public just felt that there was two types, a dwarf and a midget. A midget there's no such word, it's a slang word. Back in the early days of the circus, they had a person like myself, which is a achondroplasia dwarf, and then they had a perfect proportion person, which they used to call a midget. But his real title would be a pituitary dwarf.
Of the 1,000 or so mutations which affect our height, many are either very rare or minor variations on a handful of conditions.
I'm the most common type you'll see, the achondroplasia. It's an average size head and an average size torso. My limbs are small, so it makes me look very lopsided.
You know, there's usually somewhat of a larger forehead, sometimes protruding. Usually there's not a lot of bridge to the nose.
Well, mine would be in the lower buttocks. We all achon type of butt here, you know. It's kind of a slope thing, but the achons usually have a bubble butt.
Pseudo-achondroplasias we all tend to have more average-looking faces, and we all tend to share this kind of straight, slopey nose here, and that waddle too. I could see a group of dwarfs walk by, and if you see somebody who's waddling, I'll probably say, oh, there goes a pseudo. Pseudos, we tend to be kind of verbal and outspoken. Not all of us, but some of us.
Of course, dystrophics have the brains, right?
Oh, the brains. We have that too.
In Reno, I must have met people with any one of at least a dozen distinct kinds of dwarfism. And there were probably another dozen there that I didn't see. In the last 10 years, the mutations responsible for nearly all of them have been identified. Now that the human genome has been sequenced, the discoveries are coming faster yet. We even know the very thing that eluded Joseph Mengele. The reason for the ovitz's smallness. Mengele's experiments, brutal and pointless as they were, taught him nothing about the family or about growth. Auschwitz was liberated in 1945 by Soviet troops. Mengele disappeared, and the ovitzes walked free. And 50 years later, the gene responsible for their smallness was discovered. The family had a disorder called pseudoachondroplasia, one caused by a mutation that kills the cells of the growth zone and leaves the limbs stubby and bent. Deformity reveals normality. And pseudoachondroplasia, it's just one more mutation, one more abnormality that reveals a minute but critical part of what makes us the size we are.
Next week on Human Mutants, we look at conjoined twins, cyclops, and mermaids. The shaping of the embryo in the womb and how the plan for the body can go drastically wrong.